All right, so last thing we didn't finish up in 8.4 was finding roots. Okay, we had practiced raising numbers to powers, okay, using de Moivre's theorem. Okay, so all you have to do to use de Moivre's theorem is raise the radius to the power, multiply the angle by the power. Much faster than foiling things out, especially if you had to foil out like 20 or 30 sets of parentheses. You're probably not going to be able to do that in a reasonable amount of time. And even if you could, there's just so many calculations you'd make a mistake probably. Okay, so then we talked about what would be the reverse of what we did in example 1. Example 1 was cubing. So the reverse is cube rooting. What we have to remember when we take a root is there's as many answers as the root you're taking. So if you are taking a cube root, there are 3 answers. If you're taking a 20th root, you get 20 answers. We'll probably do 1 up to 5 answers. Okay. So first of all, this is the basic equation you want to set up anytime you're taking a root. This never changes. It's always just a z. Okay. The n and the a change depending on the root you're taking and what you're taking the root of. N is the root, square, cube root, 4th root. N is the type of root. And A is what you're taking the root of. So if I wanted to explain to somebody that had never heard of square roots before, I would say something like, well, if you wanted to understand the idea of the square root of 16, I would say that you can take some number, raise it to the 2nd power, and get 16 as the answer. If you can figure out what number you raise to the 2nd power and get 16, effectively you just figured out the square root of 16. Okay? So the idea is you have to figure out how to solve that equation. If you're solving it specifically where there is a 1 in this spot, that the book just uses a different word. They don't say take the square roots of 1 or cube roots of 1. They use the word unity. So if that's confusing, you really could just replace the word unity with 1. Okay? This is finding the nth roots of 1. Okay, so I think what I'll do is sometimes I skip the steps and just show the example. Maybe I'll show the steps and I'll do the example like at the same time. Because just reading the steps, it doesn't really make sense. Really, I think the example is what helps it kind of click. So, let's go like this. Okay, so we're going to start out by finding, you know what, let's do, I have a different one. Yeah, we'll do the cube roots of, we'll do 2 of them. Let's start with the cube roots of -8. Okay, so let me delete the stuff in between. Okay, so how do we find, where did my cube roots go? The wrong page, delete. I'll just write it myself, it's fine. So we're going to find the cube roots of -8. So the first thing you want to do is set up that equation, z to the power equals a. Keep in mind, z and a can be complex numbers. Okay? We're not just dealing with reals, we're dealing with imaginaries. Okay, so I'm gonna set up that equation. So z is going to just stay as a z for now. And now the exponent is the power, or it's the root you're taking. So we're doing a cube root. And what are we taking the cube root of? -8. So if you can solve that equation, you will have figured out the cube roots of -8. Now, when I go to solve it, how many answers am I expecting? Yeah. Yes, we're going to have 3 answers. And we're going to write our answers in trig form. Okay? If you want to convert from trig form to standard form after, that's just a matter of taking what's on the outside and distributing. Okay? Like, if you wanted to convert this answer to standard form, you just do this out and change everything to decimals. Okay? That part would be easy. But as we work through this whole process, we'll use trig form. So, to write it in trig form, we have to change the z and the a, which remember, those are both complex numbers, into trig form. Technically, you could go like this if you want. That's standard form. It's -8 plus 0i. So what I'm going to do is change the left-hand side and the right-hand side into trig form. The left-hand side is where all your variables are. Okay? That's where the z is. So a is an actual number when you do the problem. It's -8 plus 0i. So for the left-hand side, you're always going to do this. You're always going to change z to r cosine theta plus I sine theta. Now on this side, I put r1 and theta 1 only because I have 2 things that are generic. Right? And this is just kind of the general formula. I don't have any specifics. In this formula, I do have something specific. So the other side is not going to be an R2 and a theta 2. We're going to figure out what R2 and theta 2 are based on that right there. Okay, we're going to find the radius if we graph that point and the angle. Okay, but the other side, you always just leave it the way I did. Now, -8 plus 0i, that's an easy angle to find because it has a 0. It's on an axis. So if I want to graph -8 plus 0i, starting at the origin, which way do I go? Sam? Which way?
Left.
Left, and how many?
8.
Yeah, we go left 8. So we're over here. And if we go left 8 units, Dylan, how far are we from the origin?
You're still 8 units.
You're 8 units away. If you move on an axis, you don't need Pythagorean theorem to find the radius. So the radius of this is 8 cosine. And now I need the angle. Jay, and if I'm on the negative x-axis, what's the angle?
It would be 180.
180. So we just converted the right-hand side into trig form. So 8 cosine 180 plus I sine 180. Okay, so now, effectively, you have something like this, except in your problem, R1 and theta 1 and n are all actual numbers. This is how it would look generically. That's why I think it makes more sense a little bit when you have the numbers. Okay, so now, at this step, you've got a left-hand side equals a right-hand side. Each side has a radius. And each side has an angle. In order for the left-hand and right-hand sides to be equal, what's in the red boxes and what's in the green boxes has to match. Okay? So that's going to be the goal. We're going to try to make those 2 things match. But first, we have, if I want to be a little bit better with my notation, I should write it like I did on the right-hand side. In order to raise this number to a power, or I'm sorry, raise this complex number to a power, what would we do with the r and the 3? Using what we learned yesterday. Yeah?
We raise the r to the same power.
Yeah. Raise the r to the power. And what would we do with the theta and the 3? Yeah, Rebecca.
Multiply it by 3.
You multiply. So sometimes people just do that step out and they don't even bother with the step above it. They jump to what I'm writing in black right now. I'm just going to put equals, and I'm not going to write down the right-hand side again. So now we have r cubed cosine 3 theta plus I sine 3 theta. Okay. Generically, you would have something like that. The right-hand side stayed exactly the same. You raised the r to the power. You multiplied the angle by the power. Okay. Now we're at the step where we can set up two equations to make the radius on the left match the one on the right. So we're going to take this and set it equal to that. So in my problem, r cubed equals 8. That's what we would write. Okay, we'll solve that in a minute for r. Probably already know the answer, but we'll find our radius in a second. And then the second equation is when we set the angle equal to the other angle. That's what you start with. So 3 theta equals 180 in our problem. Angle on the left equals angle on the right. But we have to remember that when we solve a trig equation, there's multiple answers. So to represent all the answers, we have to put plus 2 pi. I think we use the letter n. It doesn't really matter. I'm just going to leave it as k. But you have to put plus 2 pi k. If you're doing radians, or if you're doing degrees, plus 360k. So what this does is represent all solutions. Okay, and we've done that kind of thing before. Any questions why I did 360k on the right and I had 2 pi on the left? It's just a matter of degrees and radians, and this problem's in degrees. So, okay, now we solve each equation. So to get r by itself on the left, cube root, and what's the cube root of 8? Okay, 2. So now, when we write all three answers, they all have a radius of 2. 2, 2, 2. If the radius is the same, then what's going to be different to give me 3 different answers? Yep, the angle. The angle is the only thing that can be different because it has a variable in it. So what do we do with k? Very easy. All we have to do with k. So this idea I already explained to you. We have a single radius, and all the values have the same radius, but it's the angle that's different. Okay. So an nth root has n answers. Cube root 3 answers. Fifth root 5 answers. So the way you find all the answers is you let k equal, start at 0, and count up as many answers as you need. If you need 3 answers, k is going to equal 0, 1, 2. The key is remember to start at 0. Don't go 1, 2, 3. 0, 1, 2. There's your 3 answers. So the last number that you're using for k is 1 less than your root. We're doing a cube root. The highest value for k is a 2. That's why it has this minus 1 there. If I was doing a fifth root, I would do 0, 1, 2, 3, 4. 4 would be my highest number for a fifth root. All right, so what I would probably do is it's a little easier if you just get the 3 on the other side, so then you have theta by itself. But this is essentially what you need to do at this point. If you don't want to get the 3 by itself now, that's fine, but you're going to have to at some point. So probably decent idea to do it now. So divide everything by 3. And we get 180 divided by 3 is 60. plus 120k. Okay, so let's start with 0. 120 times 0 plus 60 is how much? Yep.
60.
60. That's your first answer. Second answer. 120 times 1 plus 60 is how much? Yep.
180.
180. So 180. I sine 180. And 120 times 2, that's 240. 240 plus 60 is 300. And those are your answers. So one of those answers I would think everybody could get right away. Find the cube roots of -8. If I asked somebody that in like Algebra 1, what do you think they would say? What's the simplest answer for the cube root of -8? If they were just going to give me one answer, what number do you think they would tell me? We know there's 3, but they probably wouldn't tell me the other 2. They would say -2, because -2 times -2 times -2 is -8. But if you look at these, I don't have -2 there, right? But maybe I do. Look at that middle one. If you were to do that middle one out, 2 cosine 180, okay? And actually put it in degrees first. So put it in degrees. 2 cosine 180. I get -2 plus, let's do 2 sine 180. I get -2 plus 0i. -2 plus 0 is -2. So that's -2 right there. The other 2 answers are imaginary. Okay? Imaginary answers, just like we've seen in the past, they come in pairs. So these are conjugate pairs. One of them might be like something plus root 3i and something minus root 3i, or whatever the number happens to be. Okay, but that's the process for how you find roots. Okay, it's a little weird to kind of go through the first time, but it never changes. It's exactly the same thing every time. Okay, so we'll do one more root problem, and then that'll finish 8-4. Oh, there's the cube roots of -8. Let's do this one. The 5th roots of 1 plus I. And the first step would be to just figure out what the equation is. So if they didn't give it to me, okay, I would ask myself, all right, z to the power of the root, okay, 5th root. And what am I taking the root of? 1 plus I. Okay, before I go any further, how many answers am I expecting to get here? Yep. 5. None of them are that easy to just do in your head. Okay, it's not like, the square roots of 16, where you can just figure them out in your head because it's easy. These are 5th roots and they're complex numbers, so we gotta fix that. All right, so first thing we're gonna do is exactly what we did right here. Fill in exactly what I just circled, except now it's to the 5th power. It's r cosine theta plus I sine theta. And that's all to the 5th. And now we need to change 1 plus I into trig form. Okay, if we graph 1 plus I, it's right 1, up 1. Right 1, up 1. Right there. What's going to be the angle? I could, if I don't know it, I could do inverse tangent of y over x. Think of it as 1 plus 1i, so it's inverse tangent of 1 over 1.
That would be 45.
Yeah, the angle is 45. And, oh, that was not good the way I wrote that. So you wanted the parenthesis in front. So we have cosine 45 plus I sine 45. And what about my radius? Leo?
The square root of 2.
Square root of 2. Okay. So what I'm going to do, just to avoid rewriting it, I'm just going to raise r to the 5th and multiply 5 by theta. If you want to rewrite it and don't do it that way, that's fine. It just saves me having to write the whole thing again. Okay. Now I can set up my two equations. Radius on the left equals radius on the right. Angle on the left equals angle on the right. But what do I have to add to the 45 to represent all the solutions? That would, if I just did that, I'm only going to get one of the 5 solutions.
Plus 360k.
Plus 360k. And to get the 5 solutions, k will equal, yep, 0, 1, 2, 3, 4. If you want to divide everything through by 5, you can also do that, but we'll do that in a second. Okay, let's look at the left. So the easiest way to solve this, you could say, well, should I just take the 5th root of both sides? You could, but then you're going to have the 5th root of the square root of 2. You're going to write that a little nicer. You can't. This is not a good final answer. So what I would do is think of the square root of 2 a little differently. When you take a square root, it's the same as raising to what power? Yep. The 1/2. And now what I would do is raise each side to a power, because remember, when you have a power to a power, you multiply. The goal is to get r to the first power. You want r by itself, no power other than 1. So what could I raise each side to get rid of this 5? And keep in mind, power to a power, you're going to multiply. Yeah? Yeah, raise it to the 1/5 power. 5 times 1/5 is now just r to the first. You have r by itself. And what's 1/2 times 1/5? Yep. 1/10. That's a much nicer answer than writing the 5th root of the square root of 2. So that's r to the r equals 2 to the 1/10 power. Or if you'd rather put it as a root, when you divide, whatever you divide by, that's the root. So when you have it to a 1/2 power, that means you were taking a square root. 1/5 power is a 5th root. 1/10 power is a 10th root. 2 to the first power divided by 10 is the root. So you can write the answer like that. Mm-hmm.
So if you, say for dot, you were able to do that, if you had the 5th root plus the square root of 2, could you just multiply the 2 and 5 and have the 10th root of 2? Does that work?
So you mean multiply like the indices together? Yeah, I guess you can multiply indices. I'm trying to think if there's ever a case where that wouldn't work. But yeah, if you can think of it that way, that's even simpler. I guess, yeah, if you think of that, that's kind of like a shortcut, and this is the reason why the shortcut works. Yeah. So like if you had the 8th root of the square root of 9, that should be the 16th root of 9. Yep. Yep. And the reason why, I just showed you why. It has to do with power to a power, allowing you to multiply them together. Okay. Yeah, that's good. Okay, so we can write all our answers. They're all going to be the 10th root of 2. This is why I wouldn't have you do more than like a 4th root or a 5th root, because it just gets kind of time consuming. And I kind of get messier as I go. So cosine, 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 cosine. Okay, now we need all our angles. Let's divide through by 5 first. set? So 45 divided by 5 is 9. 360 divided by 5 is 72. Okay, now just plug in 0 through 4. If we don't need to do them all, we just do a couple of them. What would the first one be when you plug in 0? 9. Cosine 9. Pi sine 9. The second one, 72 times 1 is 72. 72 plus 9, 81. Okay. Any questions on how you would do the rest? So k equal 2, k equal 3, k equal 4. You're basically just adding 72 each time because you get an extra multiple of 72. And that's how you find roots. Okay, so probably the toughest thing to do in trig form, but there is a method to it, and you just follow the same method every time. Okay, so that would have been the homework, and you guys already did like up to 12, I think, so you would have had those 6 or 7 other questions at the end. We're going to hold off on that because we're going to do the take-home test instead. All right. So next section is 8.5. It is totally different than 8.4. It has absolutely nothing to do with what we did in 8.3 and 8.4. It's on vectors. So how many people are in physics? I know I've heard some people talk about physics stuff. Okay. So a vector, you might have studied up. I think the other class said they have, so if you're in the same physics class, you probably have too. But a vector is basically a quantity that has a magnitude and direction. Two very common examples that we use vectors to represent in real life are forces and velocities. Okay. Both force and velocity have a magnitude. For velocity, you can think of the magnitude as the speed. For force, you can think of it as how hard, like you're pushing on something. And they both have directions. Okay? If I'm pushing on this table, it makes a difference if I'm pushing down with 50 pounds of force or I'm pushing up with 50 pounds of force, or pulling up. Okay, so I can change the direction of my force. I can also, with velocity, change the direction I travel. If an airplane is flying east at 500 miles an hour, that's different than flying west. Opposite directions. So visually, we can represent a vector with an arrow. So an arrow is good because it has a point on the end. And the direction the arrow points, that's the direction of your vector. How do you think you would represent magnitude with an arrow? If you had one vector that had a bigger magnitude than the other, what would be the difference in the arrows? Let's assuming they're both traveling in the same way. Two cars traveling east, one's going 50 miles an hour, one's going 20 miles an hour. So they both point the same way, but what would be the difference with the arrows?
The length.
The length, yeah. So the length of the arrow represents the magnitude. The arrowhead indicates the direction. So a good example of that is with a velocity vector is thinking of airplanes. Okay, so I'm going to show you a picture online that shows some of the airplanes and kind of tracks where they are in real time. They don't have different length airplanes to show how fast the plane is going, but they do have like you can click on it and see the speed. Okay, but keep in mind this doesn't really show different size airplanes for the speed. Okay, so here's a map of probably some of the planes that are flying right now. Keep in mind this is three-dimensional, so that kind of adds another level of complexity to it. We've got all these different planes. We can definitely see a lot of patterns, like in the area by Providence, coming up to Providence Airport from Connecticut. Looks like there's a pretty steady flight path there flying into Providence. Can kind of tell where airports are. There's like a big cluster of planes there. But all of these planes you could think of as vectors. They all have speeds. They all have directions. Direction for an airplane uses compass headings. So a plane like this one, right there, looks like it's traveling east. That would be a heading of 90 degrees. Okay? It's pretty straight to the east. So if we look online, we should be able to see something about its flight path or its route. And the route here looks like it's encoded with some kind of code that they use for flying. But I bet if I click it and decode it, I'll see a lot of headings around 90 degrees, 80, 100. Yeah, so once the plane got going, the heading is 80, 91, 100. And that's just showing different turns. So it looks like it's a pretty straight path, but the plane is really taking a bunch of turns. And you can see how many miles, maybe? I'm not sure. But it shows distance it traveled on that leg. Could be miles, kilometers. And then, like maybe what tracked it, a waypoint. Maybe that's just some kind of station on the ground that tracks the direction. But the point is it has a direction, and it has a speed. So that plane was traveling, I thought it said the speed somewhere, 442 miles an hour. Okay. And it might not be traveling straight to the east. This one might be gaining altitude as well. So it's traveling east and up at the same time. Okay, so it's getting higher. So it's, yeah. All right, so any questions on that idea? And it's the job of an air traffic controller at the airport to kind of coordinate all this traffic coming in and out, landing, taking off, and kind of keep everything moving smoothly. So there's definitely a lot of planes in the air. It's got to be thousands at any one time. Maybe tens of thousands, hundreds of thousands, I don't know. But it's a lot of planes. All right, so let's go back here. All right, so if we have 2 points, we can kind of do this on a grid to do an arrow, where the 2 points are our initial point and terminal point. And a vector is always drawn from the initial to the terminal. Okay, and in geometry, you can call that an arrow, but a lot of times we call it a ray. Okay, because it just goes in one direction. One way to represent this vector, like if I wanted to discuss this in geometry, I would say ray PQ. When we're talking about it as a vector, we could use a single letter on paper. You could use ray PQ notation as well. But this is another notation you can write down. And when you use a letter, we got to be careful because we already use letters for variables. A vector is not a variable. A vector is a vector. So if you want to use a letter, you've got to make it look different than a variable. 2 ways to do that. 1, put an arrow on top. This arrow has nothing to do with direction. This arrow is just a generic symbol that means whatever letter is below it is a vector. And the arrow always points to the right. That's just the symbol. It's kind of like when we looked at this plane. It has a little altitude symbol here, and it has an arrow going up and to the right. Well, it doesn't necessarily mean that the altitude is going up and to the right. Maybe if a plane was flying towards California, from our perspective, that's west. But I'm sure they probably use the same symbol, just meaning it's just going up. Okay, that's all it means. Okay, the same idea here. Just an arrow pointing to the right is a vector. Or you can make it a bold letter. Okay, either way. If you look in the packet, I think they mostly use bold letters. All right, so one thing we want to understand is what happens when you add 2 vectors. Okay, if you look at it from a force perspective, if I push on the table towards the door, exactly towards the door, not down towards the floor or up, but I just push exactly horizontal with 50 pounds of force, and somebody else over here pushes exactly horizontal with 50 pounds of force, effectively, that's like pushing on the table with 100 pounds of force in the same direction. So what happens when you combine two vectors together, you get a new one. Depending on how the vectors are interacting, the direction can change. Imagine an airplane flying east at 500 miles an hour, and it's flying into a northeast wind at 100 miles an hour. So now the wind is going to blow the plane. Sometime if the plane is flying into the wind, it can change the direction of it and slow it down. If the plane is flying with the wind, then it can speed the plane up, but it could also change the direction of it too. So like if you had a plane flying north and a wind blowing northeast, well, what's going to happen is the plane is going to speed up a little bit because the wind it's kind of working with the plane, but it's also going to blow the plane off course. So the pilot would have to adjust the vector for the plane to make sure they go where they want to go. So that's the idea. When you add two vectors together, you get a new vector. Okay, so I'm going to show you how to add two vectors graphically. Okay, I'm just going to demonstrate it first, and then I'll write out how to do it. Okay, if that's vector v, that's you, and that's vector w, basically to add these together, you connect the terminal point of one to the initial point of the other, just like that. So you line up, if I'm doing v plus w, I would do it like that. If I was doing w plus v, I would do it like that. Does it make a difference? We'll talk about that in a second. Okay, but I'm going to put it back as v plus w. So the end point and the beginning point line up, and then connect the diagonal from the start to the finish. And what I'm going to do is just pull it away from there so it's kind of on its own, separate. And what I just drew in green is v plus w. That's the vector v plus w. Okay, or I guess you could also write it this way. Okay, any questions on that? Okay, so what did I really do? If you don't understand it or you want to write it down, you can. But you line up the vectors so that the ending point of v is on top of the initial point of w. So that's how I lined them up. And then I drew in the diagonal from the initial point of v to the terminal point of w. If you draw it the wrong way, you're going to get the right length, but you're going to get the wrong direction. So you have to follow that last sentence exactly the way it says to there. Okay. Any questions on that idea? And drawing is good for now. Drawing is great when you have a word problem because you need to visualize what's happening. But if I just want to add two vectors together, I would rather do it with just numbers somehow. So eventually I'm going to show you how to draw, add, subtract, and multiply vectors with just numbers. Okay, because graphing requires a little planning ahead. Because if you want to add these two vectors and I want to keep it on the graph paper, I've got to start at a spot that I think I won't go off when I finish. So I can kind of see v goes down to the right, w goes to the right, so I should start way on the left edge of my graph paper. So I'll take v, actually I might even put it there. Put v there, then I'll put w on the end of it, and now I'll just draw in my diagonal. Try to draw it as straight as you can. And that's it. That's v plus w. And just pretend these are bold. You don't have to separate it off the picture when you're done. I just moved it so you could see the answer. So the answers to these kind of problems are a drawing. They're a sketch. Questions on that one? What's going to happen when we add these together? Yeah? Okay, now what did I say? When we add two vectors, the answer is always a what? When you combine two vectors, you always get a...
New vector.
Always get a new vector. So the answer here is going to be 0, but it's going to be what we call the 0 vector. That's going to be the answer. Or you could write it this way. Very important, you don't put the number 0, because the answer here is not the number 0. So if you're wondering, well, how does that happen? Well, line up the ending point of V with the starting point of W. And once you line those up, then you're going to connect where you started to where you stopped. But what's going to happen is the start and the stop, the green dots, are going to be exactly on top of each other after lining up the red dots. So there's nothing to connect, nothing to draw. So the 0 vector is kind of weird. It's kind of an exception. It's the only vector that it does not have a direction. And it doesn't have a magnitude. There is no length to it. It's 0. So don't think about it too deep, but it's just an exception, and that's what you call this situation, the 0 vector. Okay, so vector addition is commutative and associative. I will show you that it's commutative. I'm not going to go through associative. So I asked you earlier when I was adding two vectors, does it matter the order? And I said I'd show you, and now I am. And the answer is no. You can add them in any order you want. And if you're thinking, well, yeah, isn't addition always commutative? You can't assume that what you know about numbers works with vectors. For example, multiplication. Everyone should know multiplication is commutative. 5 times 2, 2 times 5, same thing. That doesn't work with vectors some of the time. Okay? If you multiply vector v times w, or w times v, you can get different answers, depending on the kind of multiplication you're doing. So, can't assume that anything you know about numbers directly translates to vectors. Some things do. Okay. So let's look at v plus w. So it's going to be kind of hard to draw this part. If you really have what's in the box, you're probably good. But I'm just going to show you why the box is true. So here's v. Here's w. And as straight as I can, that's v plus w. Okay. Now I'm going to do it the other way. I'm going to do w, and I'm going to put v on the end of it. Draw that. That's w plus v. But if I did a reasonable job, they should look pretty much the same. Okay? So I'm just showing you that it is commutative. Okay, any question on that? Okay, associative means you can change the order, like the grouping. So here, you're doing the a plus b first, and then adding c. On the second side, you do b plus c first, and then you add that onto the end of a. Associative property, just like with addition, it works just fine with vectors. So just copy down what's in the box, and you're good. The a, b, c there are meant to look bold, to represent vectors. Okay, we kind of already touched on this visually, but this is more just a notation thing now. What's the difference between the two vectors I have up on the board? Vector v and vector negative v. What's that?
Will they be going opposite ways?
Yeah, the direction is opposite. What's the same about them? Yeah,
Magnitude.
the magnitude. So the difference is the direction they point. More specifically, they point 180 degrees in the opposite directions, but they have exactly the same magnitude. So, I gotta be careful, because what I just wrote there technically is wrong. Not the sentence part, the equation part. There's something wrong in this equation. What did I write right here that's wrong. Yep.
You wrote 0 as a number and not as a vector.
You can't add a vector to a vector and get a number, and that's what I'm saying right there. When you add a vector to a vector, you get a vector. Okay? So I mentioned that earlier. Make sure you write it down the way I have it there. Okay, so to subtract two vectors, you can do this with just arithmetic. We're going to do it first visually. And I want you to think of it kind of like you would do this problem. How could you change 3 minus 2 into an addition problem? Because we already know how to do addition. And if we can change subtraction to addition, that's the key. Yep?
Negative 2 plus 3.
Okay, so you could think of it as negative 2 plus 3. Could you just keep the order the same? Keep the 3 first and the 2 part second?
3 plus negative 2.
Yeah, so all you have to do is add the opposite of the second number. Well, when we're dealing with vectors, adding the opposite of the second number, opposite just means we have to change the direction. That's all. So change the direction of the second vector, spin it around 180 degrees, and then add it. And by spinning it around 180 and adding it, you're really subtracting. Okay, so that's how we do subtraction. Okay, so find the opposite of the second vector and add. Right. So if we're going to do v minus w, the first thing I need to find is minus w. If I had a tool I could just rotate 180, I would do that. I don't. So what I can do is copy it, reflect it horizontally, and reflect it vertically. And if you do 2 reflections the way that I just did, it effectively rotates 180. Okay, so now I'm going to think of this as addition between vector v and vector negative w. So I'm going to take v, I'm going to take negative w, and I'm going to add them up. Okay, I'm not sure if I mentioned this, but when you position your vectors like this, they should always follow a path. If you ever end up with like a collision where 2 things would be coming in like that, that's not right. Okay? It should always follow a path just like that. And the answer would be what I just drew in red. And also another thing, you can add as many vectors as you want this way. Like if you wanted to add this one to this one to this one to that one to that one, that's fine. You just stack them all together and connect where you start, ultimately, to where you stop. And that's your answer. So you can stack as many together as you want. Any questions on the subtraction? All right, so we got that. Scale. What does it mean to scale something? Oh, Tessa? All right, it has something to do with lengths, yeah?
So it has like a constant factor.
Like a scale factor?
Yeah.
So what does a scale factor do to like a drawing or an object?
It increases the length of every part equally?
Yeah, it makes a larger version of something or smaller. Like if you were making a diagram of a cell, you'd be making a scale larger version, probably. Or if you were making a blueprint, that's probably a smaller version. Unless your blueprint's really the size of the house. That'd be big. So when we multiply a vector by a number, like 3v, what I just did there, that's called a scalar product. The number that I multiply by in front is my scalar. That's what I'm scaling the vector by. The result is a new vector. How would the vector v compare to 3v, you think? Yeah?
I think 3 times longer.
Yeah, it would just be 3 times longer. There would be no change in the direction. Now, if I did a half v, that would make it shorter. But there is a way I can multiply by a scalar and change the direction. What kind of number would I have to multiply by and that would change it? Yep, please. A negative. So when you do a scalar product, 3 things can happen. If you multiply by a fraction greater than 1, you lengthen it. If you multiply by a fraction less than 1 and greater than 0, you shorten it. If you multiply by a negative, you flip the direction. Right, so if I did this, now I've tripled the length of it and flipped it 180 degrees. So the point when you scale a vector, you get a new vector. A new magnitude and potentially a new direction. All right, so visually, if you ask me to find 2v, the easiest way to do that is just think of it as v plus v to get it exact on paper. Take a copy of v, another copy of it, stack them together. There's 2v. To get 1/2 v, and I really don't have a nice way I can do that exact on the smartboard. I mean, I could measure, but I'm just going to estimate. And that's 1/2 v. Any questions on those two? Graph paper, you can do this exact if you have it. All right, I'm just going to do negative 1/3 v. Okay. So can someone just describe to me what's going to happen with negative 1/3 v? It's going to take v and do what?
So it's going to be 1/3 the length and opposite direction.
Yeah, it's going to be 1/3 the length. So if I just kind of think about kind of dividing that into thirds, and it's going to point exactly the opposite way. So it's 1/3 the length, pointing the opposite way. Okay. Question on that? All right, so let's take something like that. Let's just do the first one. We'll skip the second one. So this is combining a scalar product with addition. It's 2v plus 3w. So the way I'm going to do it is kind of like I just showed you right here. I'm just going to stack a bunch of vectors together until I get what I'm looking for. So I got to kind of plan ahead though. V goes up and to the right, W goes down and to the right. So I should start on the left side, probably right in the middle. So how many copies of V do I need to stack together? Okay. 2 of them. So 1, 2. So 2 V's. And if we're doing the first one, how many copies of W? Yeah. Great. So I'm going to take 3 of those. And just put them on the end. And if I do this on graph paper, and I assume that I ended right on a nice grid line, I could actually find the magnitude using the distance formula. Just figure out the coordinates. You know, you could put your x and y axis wherever you want, and then figure out or use Pythagorean theorem down to right however many we went. And we could get the length. But for now, we're not finding the length. We're just drawing it. Questions on that one? All right. So, speaking of length, there's a symbol that we use, and if you see a vector with double bars around it, that symbol means they want to know the magnitude of the vector. So that symbol means magnitude. What would be the difference between, oh, I should mention too, it's always positive. Because magnitude is a distance, there's no such thing as negative distance. What would be the difference between those two? The magnitude of v and the magnitude of negative v. Yeah. They're the same. There's no difference between those two things. It's just measuring the direction the other way. Think of like measuring the distance from here to your house and then measuring the distance from your house to here. If you're flying like by a plane. Because maybe if you drive, you have one-way roads and you can't go the same way. But if you could just fly directly from here to your house, it doesn't matter which way you measure the direction. It's the same. If the magnitude is exactly 1, we call it a unit vector. Just like when we had a circle with a radius of 1, we called it a unit circle. Well, if a vector happens to be exactly 1 unit long, it's called a unit vector. And we're going to talk more about unit vectors next time, but that's all I'm going to say about it for right now. Any questions on the symbol for magnitude or that definition of a unit vector? Okay, so the last thing we're going to look at. If we want to start doing more complicated things with vectors, drawing is going to be hard, especially when we get into 3D. Okay. 3D sketching is not that easy, so we've got to have a way to represent vectors besides drawing them. I'm going to show you 2 ways, one today. One way is what your book refers to as an algebraic vector. And it has this notation. Angle brackets, 2 numbers with a comma between them. Here's an example of a number or a vector in that notation, 2, 3. So what do the 2 numbers represent? They're the components of the vector. It's the horizontal and the vertical component. So basically, from an initial point, that's the one thing this notation doesn't tell you. You can start anywhere you want. But from wherever you start, you go left or right, depending if it's positive or negative, A units, and then you go up or down, B units. To get to the terminal point. So think of A and B as directions. Put your pencil anywhere you want to start, and then follow the directions that A and B give you. Left and right, up and down. You don't really have to write the next part. I mean, you should know left and right is horizontal, but if you weren't sure, left and right is your horizontal, up and down is your vertical. Okay, so I'm going to go back to the second page. I'm going to look at the vector that I have there, 2, 3, and I'm going to draw it. And I'm going to come back to this page again. I would double page it, but my board's weird right now. So 2, 3. Let's start here. Right, 2, up 3. That's a perfectly acceptable drawing for vector 2, 3. Or you can copy and paste that anywhere that you want. 2, 3. 2, 3. You can even cross an axis. Doesn't matter. Those are all the vector 2, 3. But where do you think a common place to start is? Not any of the ones that I just did. Yep.
The origin.
The origin. So this notation doesn't tell you where to put it. You put it anywhere you want. But if you start at the origin, then what you have is called a position vector. And that's the last thing we're going to look at. How do we calculate a position vector if it's not at the origin? And it's super, super easy to do. Okay. In fact, I'm going to put the other picture back up on the screen. And then we'll come back to this and I'll show you how to find a position vector. Okay, so let's put one in the first quadrant just to make numbers easier for us. And pretend these two don't exist. And all I'm going to do is tell you the initial and terminal points. So we've got 2, 3. That's the initial. And 4, 7. That's the terminal. Now, does anybody see what you could do with those coordinates to turn it into that vector? Yeah.
Subtract the initial from the terminal.
Subtract the initial from the terminal. Kind of bad that I had the initial point be 2, 3 and the vector came out to 2, 3. But no matter where you put it, the idea is if you do 7 minus 3 and 4 minus 2, that's how you get this. 4 minus 2 is 2. 7 minus 3. Did I count them? 1, 2, 3. 1, 2, 3, 4, 5, 6. 4 minus 2 gives you 2. 6 minus 3 gives you 3, as long as you label your points right. So you subtract them, and you have to do terminal minus initial. And that's the last thing. I'll just write that as a formula. So if you have an initial point and a terminal point, to find the position vector, subtract the x's, again, terminal minus initial, and subtract the y's, terminal minus initial. If they don't tell you which one is initial and terminal, always assume point 1 is initial, point 2 is terminal. Okay, so I'll just show you a quick example. A terminal, initial, if you subtract them, you get 5. Terminal, initial, if you subtract them, you get 4. That's how you do it. So you just subtract them. I'd show you the formula again, but I can't. All right. So the homework is not in the book. So the homework is the take home. It is due Monday. That's Monday, the 19th. At 8 a.m. question time. Either bring in person, or if you're on co-op or you're out, email. Do not leave it in my mailbox. Or under door. Sometimes things disappear. And if you say you left it under the door and it disappears, that's not good. If it's late, so if you say, oh, can I pass it in at 8:30? No. Late tests equals 0. Okay? You can use the videos, you can use your book, you can use notes, but make sure you are working on it yourself. Okay? You're not supposed to work with other people. If you are working with other people, then, and I figure that out, you will get a 0. So make sure you're working on it. Your homework. Make sure you show work. Okay? If you don't show work on a short answer question, I will not give you credit if you get it right. Okay? So like a law of cosines problem, you've got to show me the steps for how you solved it, or you will not get credit, even if your answers are right. Because you could just go on Google, type in law of cosines calculator, and just type in all the answers. So you got to show me your work. Okay. Any questions on that? Perfect.